Hello, my name is Shruti Hariyani and I'm a 2024 recipient of the Arnold Beckman Postdoctoral Fellowship in Chemical Sciences, and I'm really excited to tell you about my research during my postdoc that was focused on advancing fluoride ion batteries. To begin, I wanted to tell everybody a little bit about myself. I am a Texan through and through. I did my PhD in chemistry at the University of Houston under the supervision of Professor Jacoa Bergosh. And then I moved just down the road to College Station, Texas, where I did my postdoc and earned my Arnold O. Beckman Postdoctoral Fellowship at Texas A&M University, where I worked with Professor Sarbajit Banerjee. And due to the Arnold O. Beckman Foundation, I was actually able to visit the Paul Scherdt Institute in ETH Zurich, where I got to learn how to make battery cells. And as of January 1st, 2026, I am now an assistant professor of chemistry in the Department of Chemistry and Biochemistry at the University of Texas at Dallas. So my research was focused on battery materials, and it should probably come as no shock to everyone that batteries are everywhere. So just for an example, this is a picture of my desk at Texas A&M University, and you can see that among all of my knickknacks, my desk is actually covered in batteries, from my cell phone to my laptop to an actual flashlight that sticks on my desk and even my car key fob. And so if we really want to emphasize how many batteries we really have in our world, if we zoom out and just look at the offices in the chemistry building at Texas A&M and we approximate that there's about 200 of those offices, then we would have about 1,400 batteries. If we were to expand that even further and apply that to all of the almost 80,000 Texas A&M undergraduate students, we would have over 500,000 batteries. And if we then zoom out to the rest of the earth, now there's just way too many batteries to count. So lithium-ion batteries have become our dominant energy storage technology because of their high energy density and the diversity in which we can package these battery cells. Here I'm showing an animation of how a lithium-ion battery works. As we charge our batteries, these lithium ions move from a positive electrode to a negative electrode, and when we discharge, they move back in order to create our electrical energy. And so usually what we have as our electrodes are some transition metal oxides and graphene, and our lithium ions simply sit in different vacant sites in those two different kinds of crystal structures. And so while commercial lithium-ion batteries have revolutionized our lives, and we use them all the time in our phones and batteries, the reason why we can do that is largely because of the electrode materials. And the most common electrode materials are lithium, nickel, manganese, cobalt oxide, and lithium iron phosphate. And so the reason why, again, these are the most common is because of their exceptional properties, which I'm highlighting here on this spider chart on the left. And while you can see that they excel in terms of being really cheap and really high energy density, there are some areas that need improvement. For example, the materials used in these electrodes are not very earth abundant. So here I'm showing a table where we're asking the question, how many batteries can we make using only US reserves of these metals? And so you can see that if we're considering a nickel, manganese, cobalt oxide electrode, that we are actually really low on cobalt, and that is our limiting component. So unless if we find a way to recycle cobalt from our lithium-ion battery systems, we may run out of the cobalt needed to make these electrodes in the first place. Another area of improvement that we need to undergo in our lithium-ion batteries is their safety. Lithium-ion batteries can spontaneously undergo a process called thermal runaway, where they get really hot. And when this happens, the flammable organic liquid electrolytes in these systems can catch on fire, which poses a really serious safety risk. So for example, the BBC have reported that the electric buses that are used around London are randomly catching on fire, and so you can see that this is a problem that we desperately want to alleviate. So our short-term goal in the battery field is to optimize the engineering of our lithium-ion battery systems in order to achieve better performance. However, there are a lot of applications that we're hoping to use batteries for. So not only do we have our personal electronic devices, but we also want to apply batteries in space exploration, wearable electronics, and even grid storage. And unfortunately, lithium-ion batteries are not technically going to be the best solution for all of these different applications. So our long-term goal is to diversify our battery technology for performance that's tailored to these specific applications. And so diversifying battery technology requires innovation and out-of-the-box thinking. And this is where Dr. Arnold Beckman was truly a master. His vision and importance that recognizing that only by taking risks do you make progress was really instrumental to his success in developing crucial laboratory equipment such as the pH meter and the spectrophotometer, which are equipment that we as scientists use in our daily lives. Dr. Beckman was truly a visionary in his ability to invent these instruments, and it's my goal as a scientist to follow in his footsteps and honor the legacy that he left behind. So in my research and in an effort to diversify battery technology, I wanted to work on batteries that again did not use lithium ions, but a different charge carrier. So there were some criteria that I wanted to be aware of. The first is that I wanted to look at charge carriers that are made up of earth-abundant elements, because remember, we're trying to work away from not having enough of these elements for our batteries. In addition, I wanted to use elements that had an accessible supply chain, and 3, most importantly, they have to have the capability to match or exceed the performance of a lithium-ion battery. To choose a new charge carrier, we can look at this table of standard reduction half potentials. Here, what we're trying to do is maximize the potential, and you can see that lithium has the highest magnitude of 3.04 volts. The element that next comes closest to that magnitude is actually fluorine, which is an anion, and we don't typically think about anions when we're making our battery materials. And so it's possible that we can now use fluoride ions to power our batteries, which is similar to what we have in our toothpaste. So the reason why fluoride ions are actually really exciting for this application in batteries is that fluoride ions are really earth abundant. You can see in this pie chart here that fluorine is way more earth abundant than lithium. Not only that, fluorine has its accessible supply chain because we are regularly mining calcium fluoride here for different purposes such as powering our refrigerators and to make glass. And finally, preliminary calculations predict that fluorine-ion batteries will have really high volumetric and gravimetric energy densities. So the vision of my postdoctoral research was to identify unique crystal structures that have this unique ability to reversibly accommodate these fluoride ions. Because remember, we want the structure to accept the fluoride ion and give it back. And so I specifically focused on structures that have large one-dimensional tunnels that are empty because they're perfect for us to place a fluoride ion inside of. Some of the questions I sought to answer during my postdoctoral research were, what's the optimal tunnel size for a fluoride ion to insert? Are there any unique structural motifs that can stabilize a fluoride ion better than others? And how does the inserted fluoride ion interact with the host crystal structure? So once we have identified and synthesized our candidate materials, we had to test and see if the compound would even host this fluoride ion. Typically, to test this involves making a battery cell. However, making batteries are really non-trivial and they require a lot of effort, specifically because we have to identify the perfect counter-electrode and electrolyte for this cell. As fluoride ion batteries are still in their nascent stage of development, we don't know what the perfect counter-electrode and electrolyte would be for our materials. So instead, we have a unique method for testing our materials, and that's by using topochemistry. And topochemistry is another way of describing solution phase chemistry. So what we do is we take our candidate material and we submerge it in a solution that contains free fluoride ions. And after we allow the system to equilibrate, usually about over 12 hours, we can remove our compound from the solution and perform different characterization techniques to see if a fluoride ion was successfully inserted. And then if we're going to put the fluoride ion in, we want to make sure that the fluoride ion can come back out. So we repeat this process by treating our compound with a different solution to remove the inserted fluoride ions. In order to get a deeper look of our compounds that do and do not have the fluoride ions in them, we take our materials to Brookhaven National Laboratory where we can get access to state-of-the-art instrumentation and high-energy X-ray beams so that we can look at the specific bonding interactions in our material. What we want to do is find out how the structure of our original compound evolved in order to allow this fluoride ion to sit within the structure. I'm really fortunate to have been able to go to Brookhaven multiple times, and it's been a really wonderful experience getting to train some of the graduate students in Professor Banerjee's group on how to run these instruments too. Once we confirmed that some of our electrode materials could in fact reversibly insert and deinsert fluoride ions, the next step was to make a battery. Again, I'm super fortunate that due to the generous funding from the Arnold Beckman Foundation that I was able to visit the Paul Scherrer Institute in ETH Zurich to try and build battery cells out of our materials. Here I'm showing a picture of graduate student Victor Gomez holding the first cell that we actually made in our lab. And while it had some initial problems that we did have to optimize, we are getting closer and closer to a working prototype. While we were working on that, I was also able to present my research at the Swiss Battery Days conference and the Paul Scherrer Institute's Electrochemistry Days. And ultimately, while there's still a lot of work left to do in optimizing our fluoride ion batteries, we're really excited that we're moving in a positive direction into one day making this technology a reality. So I would not be here today without the incredible support of my advisors, my group mates, and my funding sources. Of course, I'm so grateful to the Beckman Foundation for their life-changing support, and I feel really fortunate to have such a wonderful foundation that supports young scientists. Thank you so much.